Unit 11, Lesson 2, Lesson 1 and Lesson 2 is just a buildup of information. In both Lesson 1 and Lesson 2, students are asked to take trigonometric identities and use them to simplify trig expressions. And so in Lesson 1, I went over how do we achieve this main formula, and then how do we use it to derive these next two formulas. As a reminder, I could take and divide by sine squared, divide by sine squared, and divide by sine squared, and I'd end up with this formula. And if I divided by cosine squared, and divided by cosine squared, and divided by cosine squared, I'd get the second formula. So what I want to do before we actually start practicing problems is I want to remind students of something that I saw in Lesson 1 where students struggled. We can take this first major trig identity, and I could isolate the sine squared by subtracting cosine to the opposite side. Or I could isolate cosine squared by subtracting sine squared. Let's do the same thing down here. If I wanted to isolate tangent squared, I would subtract 1 to the opposite side. So tangent squared is equivalent to secant squared minus 1. Likewise, cotangent squared is equivalent to cosecant squared minus 1. So I'm going to use these three main trig identities and the conversions I've made that are equivalent to the original equation below. Let's look at cosecant of x times the quantity cosecant of x minus sine of x. So I'm going to start by distributing. Cosecant times cosecant is cosecant squared, and cosecant times sine is cosecant times sine. It's pushed together. Now I recognize that cosecant is the same as 1 over the sine of x. So I've brought down an equivalent form of this. And now I'm going to go back to what we have. If I multiply across, I get sine over sine. Well, the sines are simply going to simplify to 1, and now I have the cosecant squared x minus 1. So let's bring this back and let's see what we have. Cosecant squared x, or cosecant squared theta minus 1, is equivalent to cotangent squared. This is equivalent to cotangent squared theta, or cotangent squared x in this case. Example number 2, tangent squared theta divided by the quantity secant of x plus 1, or secant of theta, plus 1. Now I recognize that secant theta plus 1 could be achieved by multiplying by the conjugate to receive secant squared theta minus 1. That may seem complicated. Take a look. Remember, if I multiply the numerator and the denominator by the exact same quantity, it doesn't change the value of this original fraction. For instance, if I made this the value 2 and I put 2 over 2, well, 2 over 2 just reduces to 1. So if I write secant theta minus 1 on the top and secant theta minus 1 on the bottom, and you may be thinking, why are you doing that, Miss Bradley? What does that achieve? Well, now when I multiply in the denominator, secant theta times secant theta is secant theta squared. The inside would be a positive 1 secant theta. The outside would be a negative 1 secant theta. They're additive inverses. They're exactly opposite and they cancel out. And now I'm in a FOIL at the very end. So I've done the front, the outside, the inside, and here's the last. Positive 1 times negative 1 is negative 1. Now before I go ahead and I distribute through, I want to see, is there anything else I can do? So I bring back this list of identities, and I find that secant squared theta minus 1 is equivalent to tangent squared theta. So I'm going to rewrite this expression. I have tangent squared theta on top times the quantity secant theta minus 1. This is equivalent to tangent squared theta. And now the tangent squared theta on top and bottom, remember, they don't just disappear. They're going to simplify to 1, and I'm left with 1 times this quantity over 1, or simply the secant theta. We're going to approach example 3 much like we approached example 2. I see 1 plus the sine of u, and I'm thinking to myself, oh, that'd be great if I could turn it into 1 minus the sine squared u. To do that, I'm going to multiply by the conjugate of the denominator, so 1 minus the sine of u. Conjugate means I write down exactly the front and the back, but I change the sign in between. And by doing that, when you multiply these, I have 1 times 1 minus the sine of u in the numerator. And I'll write this out just so that you can see it. But there's also a shortcut. When you go ahead and you FOIL the denominator, you only have to multiply the fronts and the lasts, because the insides and the outsides, when you're FOILing or distributing through, are going to cancel out their additive inverses. So I have 1 times 1 minus the sine of u in the numerator. On the bottom, I have 1 minus the sine squared u, and I recognize that 1 minus sine squared u is equivalent to cosine squared u. Now let's distribute this to get 1 minus the sine of u in the numerator, and now I have the cosine squared u in the denominator. How can I do this? How can I rewrite this so I have a minimum number of trig functions and I have no denominator? That's my goal if I can achieve this. So I'm going to rewrite this, but I'm going to come off to the side and just remind us how we can do this. If I asked you to take this quantity and I wanted you to write it as two pieces, you could say, okay, the 7 has to be shared with the 2 and with the 5. So 2x over 7 plus 5 over 7. We're going to do the exact same concept over here. Cosine squared u is shared with the left and the right and has separated those two quantities with subtraction. So 1 over cosine squared u subtract sine u over cosine squared u. Now, I recognize that 1 over cosine is secant, so 1 over cosine squared u is the same as secant squared u. I'm going to separate this into two parts because I see there's two of these. You guys can see that. So think of this as just like that. Think of that as we have the sine of u times 1, the sine of u times 1. So I'm going to have two parts here. I'm going to have sine of u over one of those cosines right here. See, there's 2. And here's the other cosine of u, so that becomes cosine squared times 1. If I multiplied, I'd have cosine u times 1, that's cosine u. Cosine u times cosine u is cosine squared u. Secant squared u minus, well, I know sine over cosine is simply tangent u, and 1 over cosine is the secant. Lessons 1 and 2 is all a build up to lesson 3. So in lesson 3 and 4, we're going to have a statement and it's going to equal something on the right hand side, and we're going to have to use trigonometric identities and trig functions to be able to show that one side equals the other side. So this is all a practice in getting ready to perform the tasks in lesson 3 and lesson 4. So let me show you a couple different ways that we could simplify this. One way would be to recognize that I could rewrite secant over here as 1 over the cosine squared. And I know cotangent is the same as cosine over sine. Cotangent squared is cosine squared over sine squared. I see the cosines on the top and bottom will simplify to 1, and I'm left with 1 over the sine squared. I recognize that 1 over sine squared is equivalent to cosecant squared. That's one way to simplify. But what we need to recognize is that when we move into lessons 3 and 4, and there's nothing wrong with this, but when we move into lessons 3 and 4, we may have to look at a problem in multiple ways to simplify. So there is nothing wrong with ending at this point, for example, 4. But what I want you to recognize is that it's possible in lessons 5 or lessons 3 and 4 that we rewrite this as 1 over cosine squared plus 1 over sine squared. I know secant is the same as 1 over cosine, and I know cosecant is the same as 1 over sine. Now, in order to add fractions, we have to have a common denominator. And so what I'm going to go ahead and do is I'm going to use that butterfly method. 1 times sine squared is sine squared theta plus 1 times cosine squared is cosine squared theta. Now I'm going to multiply the 2 in the bottom. Cosine squared theta times sine squared theta. I recognize that the most basic trig function I have to know is that cosine squared theta plus sine squared theta is equivalent to 1. this is equal to this. And in lesson 2, there's no wrong answer. If you're following the trig identities, using them correctly, this would be correct, and so would this. I have sine squared x plus tangent squared x times sine squared x. Well, I recognize that both the left and right contain sine squared x. So we're going to try one way of doing this. Sine squared x times what quantity is sine squared x? And sine squared x times what quantity would equal tangent squared x times sine squared x? Let's make sure that works out. It looks good. Now I'm going to come back to that paper. I realize that 1 plus tangent squared is equal to secant squared. So this is what we're looking at right now. And then I say to myself, hey, what is secant squared? Well, secant squared is the same as 1 over the cosine. So secant squared, 1 over cosine squared. When I multiply, I get sine squared x over cosine squared x, which is equivalent to tangent squared x. We're going to have to go back and tap into some skills we learned early on in the first semester. Let me replace cotangent squared x, or cotangent squared theta, with simply x. So in this case, I would have cotangent squared theta, in this case I would have x, but there would have to be 2 of them, because if x is cotangent squared, I'd need to square that quantity to get to the 4th. And here I'd have 2 times x, because again, x is cotangent squared, I have that plus 1. Now, if I asked you to go ahead and simplify this, you may recognize, oh, I think I can possibly factor this. 1 times 1 is 1, and I'm asking myself what multiplies to equal 1 and adds to equal 2. That'd be 1 and 1. And there's a couple different ways. We talked about factoring. One way is putting the A value down, and the C value down, and then in here we have 1x plus 1x. And that's how we achieve the x squared plus 2x plus 1. Okay, so let's continue factoring. I can factor out x and I achieve x plus 1. I'm going to rewrite the x plus 1, asking myself, is there a value times x that achieves 1x? Yeah. 1 times x is 1x, and 1 times 1 is 1. So the left and the right both contain the x plus 1, and the front part is an x, and the back part is a 1. I have the same quantity squared. Now, really, what was x? X was really cotangent squared. X was really cotangent squared. So I could write this as cotangent squared theta plus 1, and I'm going to write it down twice. Cotangent squared theta plus 1. What is cotangent squared theta equal to? Cotangent squared theta is equal to cosecant squared theta minus 1. Cosecant squared theta minus 1. I recognize that cotangent squared theta plus 1 is the same as 1 plus cotangent squared theta. 1 plus cotangent squared theta is the same as cotangent squared theta plus 1, right? I just flipped the 1 and the cotangent squared. Well, they are equivalent to cosecant squared. So this is equal to cosecant squared, and this is equal to cosecant squared theta. Cosecant squared theta times cosecant squared theta. Keep the base, we add the exponents. Number 7, I'm going to start by writing this in standard form. It's not necessary, but I think it'll help us out. Same signs have to follow each term. Okay, now just like I did with example number 6, I'm going to say that x is going to be equal to the cosecant squared of theta. So when I rewrite this expression, I have x, and I have to square it. So here is cosecant squared, but I need to get to cosecant to the fourth. So 2 times 2, a power to a power we multiply, is 4. Minus 2 times x plus 1. Let's come off to the side to see, can we go ahead? And this is often referred to as U substitution. Right now I'm using x because I'm not with you in class to demonstrate in person, but I will give you some examples like this in class when we return. Okay, what multiplies to equal positive 1 and combines to equal negative 2? That would be negative 1 and negative 1. Multiplies and combines. Okay, so I'm leaving the a, leaving the c, and then minus 1x minus 1x. This is one way to factor this trinomial. I can take out an x, and I'm left with x minus 1. I'm going to rewrite x minus 1, and in front, what quantity times x is negative 1x. And negative 1 times negative 1 is positive 1. They both contain an x minus 1. In front of the first is an x, in front of the second is a minus 1. Well, what is x? X, let me write this down twice. X is really the quantity cosecant squared theta. Cosecant squared theta. So I'm going to bring back that paper, cosecant squared theta minus 1. Is that here? Yes, cosecant squared theta minus 1 is equal to cotangent squared theta. So this is equivalent to cotangent squared theta. And this also is equivalent to cotangent squared theta. When you multiply and you have the same base, you keep the base and you add the exponents. Let's take a look at example number 8. In example number 8, I'm going to go ahead, like I did for example number 6 and example number 7, and it's called U substitution. I really should be using a U right now, but using another variable will work. So I'm going to go ahead and I'm going to say that x is equal to the secant squared theta. So if I rewrite this, I would have, think of this right now, before I even put an x there, this would be secant squared theta, but then I have to have it to the fourth minus 1. So this really becomes x squared minus 1. If I asked you to take x squared minus 1 and to write it in a different form, hopefully you'd recognize that there's no b term there. There's a missing b term. So how do we factor this? What multiplies to equal negative 1 and combines to give us 0? That'd be positive 1 and negative 1. Positive 1 times negative 1 is negative 1, and they combine to give us 0. So I'm leaving the a term, I'm leaving the c term, and then dropping positive 1x and minus 1x. Let's go ahead and factor this. And if you remember the difference of squares, it may be even easier for you to remember this becomes x plus 1 and x minus 1. But I'm showing the non-traditional or slower method of doing this. I can factor out x to get x plus 1. What quantity times x is negative 1x, that's a negative 1, and negative 1 times positive 1 is negative 1. They both contain an x plus 1. In front of the first quantity is an x, in front of the second quantity is a minus 1. Now what is x? That's what we need to achieve next. What is x? X is secant squared theta. Secant squared theta. So let's bring back that paper and let's look at our options. Secant squared theta minus 1 is equal to tangent squared. Secant squared theta minus 1, this portion is equal to tangent squared. So I'm going to rewrite this in the small space. I'm going to put that in front. Remember, a times b is the same as b times a. So it doesn't matter which quantity I write first. I know this is equivalent to tangent squared theta. And then we're going to multiply it by secant squared theta plus 1. What can I do here? Well, I recognize two completely different terms, and I'm thinking to myself, if I called this a and I called this b, and I said, what is a to the fourth minus b to the fourth? How would I go about factoring that? What would I do? So that's what we're asking ourselves right now. So that would be a squared squared minus b squared squared. And going a difference of squares, I could take a squared plus b squared and a squared minus b squared. Now watch. This gives us a to the fourth, perfect. The inside is 1a squared b squared. The outside is negative 1a squared b squared. And then the back is going to be a negative b to the fourth. So to be successful at problems like number 6, 7, 8, 9, and in fact 10, it really relies on what did you learn in Algebra 1, 2. Your foundational skills from Algebra 1, 2 are going to be the basis for you being successful on these tough trig expressions. So I'm going to do the exact same thing up here. I'm going to rewrite this as sine squared x minus cosine squared x. Does it matter if you do the subtraction first? It does not. And then I'm going to add the second one. So just like I did here, notice I have the squares. And you're thinking, why did I do sine squared and not sine to the fourth? Because when I FOIL, I want to receive sine to the fourth. So here's sine to the fourth when I multiply. The inside and the outside are called additive inverses. They just cancel out. This would be a negative sine squared cosine squared. This would be a positive sine squared cosine squared. So they cancel out. I'm left with the front and I'm left with the back. That's exactly what I want. So here's what I have right now, but I think I can go further. I recognize that sine squared x plus cosine squared x is the most familiar trig identity. So I can replace this quantity with 1. And multiplying by 1 doesn't change anything. So it's going to simplify to sine squared x minus cosine squared x. So let's look at number 2. We are putting a puzzle together. And again, all of this proper manipulation of trig identities to suit each expression as we try to simplify all leads up to us being successful in the next 2 lessons of this unit. So I'm thinking to myself, how am I going to add the left and the right side when they don't have a common denominator? When that happens, I'm going to use the butterfly method. Sine times sine is sine squared. And then I have cosine of x times 1 plus the cosine of x. And the bottom I'm going to push together as I multiply them. Okay, what else can I do? Well, let's go ahead and let's distribute this to see what we have. So I have sine squared x plus, okay, that's just the cosine of x, and this is cosine squared x, all over this exact same quantity. 1 plus the cosine of x times sine. Oh, look, I have a sine squared plus a cosine squared. Well, a sine squared plus a cosine squared is simply 1. So this is 1 plus the cosine of x over 1 plus the cosine of x times the sine of x. And notice on top and on bottom, I'm able to simplify this into 1. And I'm left with 1 over the sine of x. So 1 over the sine of x is simply the cosecant of x.